Okay, so now welcome to the last few lessons of our AP Statistics course. And here we're going to be talking about the chi-square distribution. So we've talked about inference for proportions as well as inference for means. And now we're revisiting those ideas in these last two units of AP Stats. However, we're doing it a different sort of way instead of comparing the claim. Actually, no, we're still going to be looking at the claim. So you know what? Let's just get right to it. Post-inner hiccup, my bad. All right, so we've seen that you can turn a qualitative variable into a quantitative variable by counting the number of successes and failures. However, this puts us into a compromise because it forces us into a very binary existence, and life is so much more than yes or no, success or failure. So if there was only a way to keep all of those categories, maybe there is, but not with confidence intervals. Remember, a confidence interval helps us to estimate, whereas a hypothesis test helps us to find significant evidence towards a claim. Well, confidence intervals estimate a single parameter, typically a value that we believe to be true from our own experience or historical evidence. And we don't have that with a categorical variable, right? We just have this claim proportion of what we believe is the truth. So we're not going to use a confidence interval here. Instead, we're going to use the hypothesis test to try to determine if an observed result could reasonably be expected, and to determine if there's a significant difference between that which was observed and that which was expected. And perhaps this might work, but we just need to find some way to measure the difference between an observed distribution and the expected distribution, and that brings us here to our friend called the chi-square distribution. So you can see here in a chi-square distribution, we can see that the degrees of freedom, as we previously learned with quantitative variables, we can see that as the degrees of freedom increases, typically our distribution becomes more symmetric. So we can see the difference here between degrees of freedom 1, degrees of freedom 4, degrees of freedom 8, and I'm sure you know what happens once we hit 30 and up. We get that approximately unimodal symmetric shape. Now, there are a few characteristics for using this chi-square distribution. And the thing I like about chi-square is that we're going to do an activity in class that's revolved around Benford's law. So we're actually going to try and catch some tax fraud. And we're also going to be testing these claims when, people or companies are committed to ensuring this, that these different proportions, populations are actually estimated. We can now use this chi-square distribution to see how far is that difference between what the actual story is versus what the company, the claim, or what the belief that is held. Now, the first thing is that the chi-square distribution is either non-normal or not normal. However, we saw that as the degrees of freedom increase, the distribution becomes more approximately symmetric and begins to approximate the normal model. Now, we're not going to say it becomes normal, we're just going to say that it becomes approximately symmetric, and it does follow some of those normal properties. Now, we saw previously that the distribution is right skewed, meaning that we expect the mean to be higher than the median. And because we're right skewed and we're looking at expected counts, it's not possible for us to have a negative value. It's only possible to have non-negative values. So either 0 of them happen, 1 of them happen, or we approach in positive infinity, but we're not going to have any negative proportions here. And same thing when we were looking at inference for proportions. If we're looking at counts, we can't have a negative count. Now, the probability measures the area to the right since we want to observe a difference that is as large or larger than what we expected. And we call this O minus E, which is the difference between observed minus expected, and very similar to residuals back in Unit 2 between actual and predicted. Now, the degrees of freedom depend on the type of chi-square procedure. We're going to learn about 3 specific types of chi-square procedures, and today's lesson is focusing on the first one, which revolves around the goodness of fit test. Now, a chi-square goodness of fit test has the following properties. It's used when you're measuring a single categorical variable in a single population. Typically, an expected distribution is provided, and the most common indicator of goodness of fit, or GoF, or GoF, is that there's no preference, no difference, or uniformity within the categories, or that the distribution follows a particular type of proportion. So for example, this could be M&Ms, this could be the diversity in math majors at a large university, etc. But there's essentially a claim, and we are just counting what we've actually seen based off of empirical evidence. Now, instead of using phantoms, because we're not estimating a single parameter, we're just testing multiple claims at once, we're going to use a state plan do conclude model, which most AP stats teachers already use. So for my students, this is just a little variant. It's essentially phantoms minus the p. Because again, we're not estimating a single parameter, because if I'm looking across all of these categories, remember, just by sampling variability, I would obtain a statistically significant result by chance alone. And that would happen if we kept testing this population, we kept sampling. Eventually, something's going to come up as significant when in actuality it isn't, and this could result in type 1 and type 2 errors. So in order to avoid this multiple testing problem, we're just going to switch our procedure into this more 4-step process. Now, here we're going to state the null and the alternative hypotheses. Here, the stated distribution of the categorical variable of interest is equivalent to the prescribed distribution, or it's uniformly distributed. So either it follows the distribution that's claimed, or every observation is equally likely. Now, the alternative hypothesis would be a claim against this, meaning that the stated distribution of the categorical variable in the population of interest is not equivalent to that is prescribed, or it is not uniformly distributed. Basically meaning, actually we have reason to believe it doesn't follow the claim, or we have reason to believe it's not uniformly distributed. There's actually some type of association that exists here. Again, if alpha is not specified, we'll use 0.05. And thankfully for us, our conditions pretty much stay the same. So we're going to move on to the plan phase. And here we're going to check 3 assumptions. The first being that our data must come from either a random sample or a random experiment. Remember, random sampling so that we can infer to the population, or generalize to the population, and random assignment so that we can infer cause and effect to the treatment that we applied. So that's our random condition. This also helps us to have an unbiased estimator. Next, we have independence. Now, if we're sampling without replacement, the sample size must be no more than 10% of the population. And this just ensures that the degree of dependence among our observations is now negligible, because I'm not sampling a large amount, but instead, because I'm sampling a small group and I'm sampling without replacement, theoretically, my results shouldn't influence your results. And last one, which is typically our normal condition, we're going to go back to large count since this is categorical data. But we're not going to say normal by large count or approximately normal. We're just going to call it the large counts condition, and we're just going to ensure that at least 80% of all of our expected counts are at least 5. Now, we're going to do some practice with this in case you're like, whoa, what is happening? Now, if these conditions are met, we will use a chi-square test for the goodness of fit. Notice I'm not dealing with 1 or 2 samples because I'm looking at the overall claim here. I'm looking at the overall sample makeup. So I'm not just looking at, I'm not zooming in, but I'm actually zooming out this time. So I'm really looking, what did I observe and how does this match against what do I expect? Now, the do portion is technically where we calculate our test statistic and obtain our p-value. So here, we're going to take n times p, where p is the claim proportion, and we know that n is our sample size. Now, to find the chi-squares test statistic, this value here is chi. So we say chi-square equals the sum of the observed value minus the expected value squared. Again, we square it so that we don't end up with any negatives, and this also helps to emphasize those differences. And then we divide it by the expected count. Now, again, this is the long run frequency of it. So when I'm calculating these expected counts, this is in the long run. If I repeated my procedure again and again, what would I expect in the long run average? As we know, short run events can be more sporadic. Now, for a chi-square goodness of fit test, the degrees of freedom is just equal to n minus 1, which is what we're typically used to. However, instead of looking at the total number of observations, we're going to look at the total number of categories. And lastly, since this was a non-negative distribution, we're going to find a greater than probability. So we find the probability that chi-square is greater than some value. And then lastly, since p-value is this, is lesser or greater than alpha, we either reject or fail to reject because we do or do not have sufficient evidence. So let's take a look at an example. We have counts of 256 randomly selected executives in 12 zodiac sign categories. The natural null hypothesis is that the birth dates of executives are divided equally among all the zodiac signs. And the test statistic looks at how closely the observed data that models this idealized situation. I'm not sure why it says data math. I must have been saying delta math. I just love the platform so much. But how closely the math is idealized in this situation. So do we have evidence to believe that these zodiac signs do occur equally or that they are uniformly distributed because we say they are divided equally. So here is what actually happened. When I look at these 256 executives, 23 of them were in Aries, 20 were a Taurus, 18 were Geminis, 23 were Cancers, etc. Now, in order to find the expected counts, if I believe they all occur equally, and there's 12 signs, and I have 256 total, here all I did was I just took the total amount, which was 256, and I divided it by the total amount of categories, which was 12. And that technically gives me 21.3 repeating, so 21.33, 21.333. Again, this is the long run expectation. However, since we're humans and we're computing this, of course, we're going to have some margin of error. So theoretically, if they are equally distributed, each birthday or zodiac sign should occur. I should have about 21.333 people in the long run average who have each type of sign. As we can see here, there is definitely some variation between what actually is observed at our company. Now, I will state my hypotheses here. Here, my null hypothesis is that the birth dates of the executives are uniformly distributed. I don't have any evidence to suggest otherwise. However, I believe that the birth dates are actually not uniformly distributed. So you can see here, we're not writing a parameter. We're not saying P is equal to something. Some teachers might teach P of Aries equals P of Taurus equals 1/12, etc. Here, we're just going to leave it as words. Now we're going to move on to the plan state, and we're going to check our assumptions. And we were told that we obtained a random sample of 256 executives. I can assume, although a little bit outlandish here, but I can assume that 256 executives or maybe employees is less than or equal to 10% of all execs or employees at a very large company. Totally possible. And then lastly, I'm going to check that all expected counts are at least 5, which here we see 21.33333. All expected counts are at least 5, so we can proceed with our chi-square model. And since our conditions are met, we are going to use a chi-square goodness of fit test. Again, no confidence intervals, no 1 or 2 sample, just a chi-square procedure. Now, this is the math behind the chi-square statistic. So again, this is the sum between the observed minus the expected squared divided by the expected. So for my first category here at 23, I take observed minus expected, so 23 minus 21.3, square that, divide by 21.3, plus, and we typically just show the first two and then the last one. Your calculator will do this for you, or some applet on a website. But when we do this, we get a chi-square test statistic of 5.10. In order to find my p-value, I say the probability that chi-square is greater than 5.10. I use my chi-square CDF function on my calculator. And here are my degrees of freedom. We had 12 categories. 12 minus 1 is 11 categories. So a chi-square distribution with this test statistic and 11 degrees of freedom produces a p-value of 0.9261, a sufficiently large p-value here. So I'm going to go down here, and since my p-value of 0.9261 is greater than alpha at 0.05, we fail to reject the null hypothesis, meaning we do not have enough evidence to claim that the birth dates are not uniformly distributed. Maybe our sample's just a little bit wonky, or maybe we just don't know what we're doing. But as of now, because of a lack of evidence against the null hypothesis, I fail to reject it, meaning I don't have evidence to suggest otherwise. So maybe we just had a fluke of a sample here. So go ahead and pause the video and take a look at some of the example problems below, and we'll review those together shortly. Now I know you totally paused the video and definitely worked those out on your own and aren't just looking for the answer, but alas, 'tis life. So here, the p-value for a chi-square, find it, and we know that the chi-square test statistic is 18. We have 7 different categories, degrees of freedom. 7 minus 1 gives us 6. We use a chi-square distribution with 6 degrees of freedom, finding a test statistic larger than 18. And we get 0.0062. Significantly small p-value, we would reject the null hypotheses. Next up, we were testing a claim against whether or not a university is following these claim proportions. It's just asking for conditions here. I didn't have my expected claims. So here, since I'm sampling from each of the different ethnic groups, this is a stratified random sample. I took a random sample of 500 students. I can assume there's at least 5,000 students in this population. And when I check each of these claim proportions against the 500, I'll come to realize that all of my counts are at least 5. So a chi-square goodness of fit test is an appropriate inference procedure for this data.